Okay, we're picking up where we left off in the Taylor and Maclaurin series section. So in the previous video, we were introduced to Taylor's inequality, and then we worked an example problem where we used Taylor's inequality to prove that a function was equal to its Taylor series. Specifically, we proved that e to the x is equal to its Maclaurin series for all x. And I'm saying Maclaurin series because it's not like you just prove that a function is equal to its power series one time and that's it. Well, it is, but it's more specifically, you prove that a function is equal to its power series representation or Taylor series at a certain center point one time and that's it. So I'm saying this is e to the x, the power series representation of the Taylor series of e to the x centered at x is equal to 0. But if we're going to do like e to the x centered at x is equal to 2, we have to start from scratch and create the Taylor series and then prove the equality. Okay, now if you plug x is equal to 1 into this function, you get the power series representation of the number e, which is really interesting because we've made power series representations of repeating decimals. We did that earlier in the chapter, but e is an irrational number. So even as an irrational number, we were able to represent that number as a power series. And you can imagine pi has a power series representation like this. Okay, so now in this video, we're going to look at different ways we can determine power series representations of functions, but not just representations, but functions that are equal to power series, different ways we can do this outside of just using the power series function formula from scratch. But we're going to start by doing a couple of examples that do go from scratch. So, okay. Example 3, find the Taylor series for, we're doing e to the x again, but now centered at 2. All right, so remember the steps to do this are that you make 2 columns, and in the first column you find like the first, second, third, fourth derivative of just the function. So f of x is e to the x, f prime of x is e to the x, f double prime of x is e to the x, f triple prime of x is e to the x, and just go as far as you need to until you can identify a pattern, or maybe even identify that there isn't a pattern. Okay, now on the other side, you plug in the center point into these. So f of 2 is e squared, f prime of 2 is e squared, f double prime of 2 okay, and so obviously having a center point of 0 is always nice. This isn't so bad, e squared, but previously with 0, this would be 1. Each of these would be 1, but still not so bad. Okay, but what we can see here is that the nth derivative evaluated at the center point is always just e squared. So the coefficient formula is f, the nth derivative at the center point, divided by n factorial. So here's the power series of a function formula, but notice they're not doing this. They're not saying f of x is equal to or e to the x is equal to. They're not saying that, but that's the formula. So we can do this. We can, that's a way of saying that, like, it's not equal to, but it's associated Taylor series of e to the x. But also remember that when you're putting like f of x is equal to or associated like this, it doesn't matter what the center point is. The center point doesn't come up with the function itself. So this is just e to the x is equal to something, and you can see the center point by looking at the power series, but you can't tell the center point by just looking at the function. Okay, but there's the formula. So the nth derivative evaluated at 2 over n factorial, and then you put x minus 2 to the n, the center point of 2, and there it is. There's the Taylor series representation of the function e to the x centered at 2. Okay, and then they do the ratio test. They don't show the work, but they do the ratio test and get that the radius of convergence is r is equal to infinity. And then it says that they verify that, they don't show it, but that the r sub n of x that they got from Taylor's inequality, that limit as n goes to infinity is equal to 0. So then they actually set e to the x equal to the power series representation and put for all x. The domain is all x. So, okay, we have two power series expansions for e to the x. The Maclaurin series in equation 11, so this equation here, and the Taylor series right here. The first is better if we are interested in values of x near 0, and the second is better if x is near 2. Okay, now actually, this paragraph brings up something interesting that I want to point out to you that you may not, I think you inherently understand this, but I want to point it out to you. So, yes, I think you probably already realize that, if you have like e to the x and you're going to be plugging in x values around 2, then you want to, ideally, I guess do a power series representation of e to the x centered at 2. If they're around 0, you do one centered at 0, etc. But if you think about it, though, so notice this. E to the x is equal to this. Is just e to the x. That's it, is equal to this. And also, if we come here, just e to the x is equal to this. Both of these are equal to e to the x. So what does that tell you? Well, technically, all you really need is the Maclaurin series for e to the x. Because let's say you want to, you have the Maclaurin series and you want to evaluate e to the 10th power. Well, no, you can't do that. It's not centered at 10. So what? You could put e to the anything. It's all x, e to the whatever you want into this function. Now, the farther you are away from the center, you're going to need to use more higher n value, but, so what? I guess if you got a computer, right? Computers are powerful. However, if you were putting in e to the 10th, you would have to use you could use a lower n value to get the same accuracy. If you were centered at 10, if you're trying to evaluate x, e to the x something around 10, you would have to use as big of an n value if you were centered around that point. But technically, you don't really, you could just, if you don't ever have to use anything but the Maclaurin series for e to the x, for any x, from negative infinity to infinity, for any x, as long as you're willing to use a large n value if you need it. Now, you might be saying, well, okay, that's interesting. So why do we not just have a big list of all Maclaurin series for functions and have those are used the majority of the time, unless there's a special situation where you need a lot of accuracy, so you actually have to make the function centered at another value because it's just way too far off from the radius. But like the majority of the time, we just use Maclaurin series. Well, actually, that's not a bad strategy, to be honest with you. The only thing is that, remember, e to the x, the Maclaurin, both of these actually was a special case where the Taylor inequality, the d value, was valid for all real numbers. That won't necessarily be the case every time. So, like if the d value doesn't have a high enough range for what you need, you might have to move the center point to make the d value work. So it's not just needing too large of an n value to get the accuracy you need, but you also have to consider the d value. But yeah, when you consider the example problems that we've worked so far, estimating the r sub n's and whatnot and calculating series to certain levels of accuracy, and we would just go to like n is equal to 10 and get really good accuracy. So when you consider computers, how you can actually, it'll take you a little bit of time to program it correctly into a computer, but then you can just press enter, put something into the function and press enter, and you could have n be 1,000. Then it seems very tempting to just, if there's no issue with the d value, always just use the Maclaurin series for whatever you want. If you're doing e to the 25, something like that, well, just put in n is equal to, if you just put in n is equal to 100, I'm sure it'd be good. But you could just, with a computer, put in n is equal to 5,000 or something, right? Okay. Next example, it says, find the Maclaurin series for sine x and prove that it represents sine of x for all x. So, okay, so now we want to find the Maclaurin series representation for sine of x and also prove that sine of x is equal to its Maclaurin series representation. So All right, they make these two columns, and then they write out f of x is equal to sine of x, then f prime of x, f double prime of x, etc. And they're just trying to see a pattern if there is one. So you see, okay, sine, cosine, minus cosine. Now we're back at sine. Then they come to the opposite side and plug in the center point into each of these. 0, 1, 0, minus 1, 0. And then we'll go back to 1. This is going to repeat. The next one would be 1, then 0, minus 1, 0. Okay? Then the next thing you do is you consider the coefficient. So f, the nth of a over n factorial, and this is going to be times x to the n. So you might not have every time. You might with e to the x. We knew this was like 1 or e squared every time. So you just put that here and you were done. Well, here it's a little more challenging because it's not the same number every time. So they write out the first few terms. So they get every other term is going to go away as 0, but they write out the first few terms and then identify the a sub n pattern. And then with that, they can figure out what the a sub n is. So there's the Maclaurin series of sine of x centered at 0. So now to prove this, we go to Taylor's inequality to get a estimate on the size of r sub n of x, or it's like an upper limit. So that is all about what's the n plus 1th derivative. So, okay, the n plus, so this is a little more challenging. The n plus 1th derivative, we're not really picking it to do this proof. We're not picking an n. Whenever in the next section, whenever we're estimating the accuracy of a Taylor polynomial, we're going to be picking an n. Well, here to prove this for all n, that sine of x is equal to this, we have to look at the n plus 1th derivative in general. So it's going to be one of these 4 options, plus or minus sine of x or plus or minus cosine of x. However, no matter what you plug in to either of these, the absolute value of that's going to be less than or equal to 1 for all x. So there's your capital M value. So again, so what is this saying, though? The first step with Taylor's inequality is you check to see if the criteria is satisfied and for what cases of how far away from the origin. So we're thinking about what needs to be satisfied is the n plus 1 derivative of x, the absolute value of this, needs to be less than or equal to a capital M for the absolute value of x minus a is less than or equal to d. Okay, we're centered at 0. So, okay, the n plus 1th derivative is plus or minus sine of x plus or minus cosine of x. No matter what x you input, you're going to get something that's the absolute value is going to be less than or equal to 1. Now, if we come here, does this come into play? This being the absolute value of the function being less than or equal to 1, is that the case only for some fixed distance from the center point 0? No, it's for all x. You can make d whatever you want. And the absolute value of the n plus 1th derivative of x is going to be less than or equal to 1. Okay, and d does not come into play here. Before we had m was e to the d, m is just 1. Okay, so we've passed Taylor's criteria, and we've got capital M, and we know it's for any d. So here's Taylor's inequality. Absolute value of r sub n of x is less than or equal to, so here it is. They replace m with 1, and they don't have to put any, it's for all x. When they say for all x, that's telling you that that d is any number is what it's saying. When they say for all x, that means d is any number. Okay, so there you go. The limit as n approaches infinity of this, well, this is just that limit we talked about. If you can neglect the 1s here, so you just have the absolute value of x over n factorial, of x to the n over n factorial, that's going to go to 0. So there you go. You've proven it. And again, it could be the case that it's just for some radius. This is just for some radius around A. It's not a radius of convergence. It's a radius of where this inequality for r sub n is valid, but there's no radius here for that. It's for any x. D can be whatever you want. And so there you go. So now you can set sine x equal to this Maclaurin series here. Okay, so the last two problems were just more practice in the mechanics of creating a power series representation for a function from scratch and then proving that that function is equal to its power series. Now let's take a look at the next example. So find the Maclaurin series for cosine x, it says. So we're not going to do this from scratch. It's saying we're going to go ahead and differentiate both sides of this equation. So we know how to differentiate a power series. So you get the derivative of sine x is cosine x, and then they differentiate the power series. Okay, now we know from the properties of differentiation of power series that the radiuses of convergence of between the two series are going to be the same. So the radius of convergence of sine of x, power series, was all real numbers, so is cosine x. So cosine x is equal to this power series for all x. Okay, now this confused me at first when I was learning this for the first time, and you might be a little confused as well. So, okay, but don't we have to go through the proof? How can we just all of a sudden set these equal like this? And then, okay, but so they're equal, but if we were going to use, like, later when we do a partial sum, let's say, we're going to just do the first 10 terms, and we want to look at the accuracy. I mean, can we use Taylor's inequality? I mean, what's the, don't we need to go show, like, what D values this applies to for Taylor's inequality, things like that? Okay, well, the first question about why are these just equal? Why didn't we have to prove it? How can we just make this statement? Well, okay, think about it. If we come back here, we proved this equality here. We proved it. Okay. Now, what we're gonna do is we're gonna do something to both sides of this equation, and that's at this point that's a law of math. If you do something to both sides of an equation, you don't change the equation as long as you're fully under control of whatever you're doing. Meaning that, okay, so we're going to differentiate both sides of this equation. We differentiate sine of x, we get cosine of x. That's a fact. We already learned, we proved that that's a fact. The derivative of sine of x is cosine of x, okay? So that's equal to what? Now, we're going to differentiate this power series. We've already proven that we know how to differentiate a power series, and we know what it's equal to. That's a fact. So we differentiate the power series, and we get another power series. But again, the derivative of a power series, we've already proven that that's completely legitimate. And so what are we left with? We're left with this equality. So I mean, that's it. We don't need to prove anything because this is the statement. Cosine of x is equal to this power series. Okay, now if for some reason it was the case that, I don't know if this is possible, but whenever you did the differentiation, you got something that wasn't a power series, or maybe for the first couple of terms it wasn't a power series. Now we haven't proven anything like that. That's different. Not saying that would be incorrect, but now we've ventured off from what we know to be fact. As long as you differentiate the function, and that's a fact, we know how to differentiate. And then when you differentiate the power series, we know how to do that. We get another power series. It's a power series for all n. Well, then we're done. That's it. Okay, and then like I said, you know the radius of convergence, because from the properties of differentiating power series, the radius of convergence doesn't change, but you would have to check the endpoints of, if it was an interval of convergence, you have to check the endpoints. But that doesn't come into play here because the radius is infinity anyway. Okay, now when it comes to the D value, there's no property of differentiation of power series that says that the Taylor inequality D value is the same between two differentiated power series. So if the D applied was applicable for all real numbers with sine of x, how do we know it's with the sine of x power series? How do we know that that D is applicable for all real numbers with this series? Well, whether or not it is, I'm not a mathematician. I don't know. I'm not going to go investigate that. But it doesn't matter. Why? Because we don't need to go do the proof. Now, in the next section, when we use Taylor's inequality to get the accuracy of partial sums, well then, but that depends on the n you choose. Like if you're going to do a partial sum formula or do a partial sum of the power series of cosine of x, well, if you're going to use n is equal to 10, 20, you'll go to Taylor's inequality and plug that in, and and then you'll look at the d value there. My guess is the d value would end up being the same, have the same range even after you differentiated it, but you'll look at that whenever you're using Taylor's inequality for your accuracy estimation for that specific problem you're working with. What I'm saying is you'll look and see, okay, it won't be just the general n plus 1th derivative. You'll actually be choosing an n. So you'll look and see, okay, here's the 20th derivative of my function. Okay, now is that less than or equal to a number? And then, but is that, yes or no it is, and yes if it is, but is that only for some certain d radius about the center point? And you'll just go from there. Okay, find the Maclaurin series for the function x times cosine of x. So what do they do here? Well, what they're going to do is they're going to come back to this equality and multiply both sides by x. So x cosine of x, they bring the x into the power series, simplify, and done. X cosine of x is equal to this power series, is equal to. And why is that valid? Because you can multiply both sides of an equation by x and not change the equation. Now, we've seen situations where like maybe you multiply both sides by 1 over x cubed or something like that. And so if you do 1 over x cubed times this power series, I think it ends up being, it usually is something like the first few terms aren't power series terms. It ends up being a power series only starting at like n is equal to 3 or something like that. So you could make it like you could take out the first couple of terms and then you say the first couple of terms plus, and then the sum from n is equal to 2 to infinity, and you have a power series from there. That the textbook hasn't stated as a fact. Because if you multiply 1 over x cubed times cosine of x, and then 1 over x cubed times the power series, the first thing you get is something that's not a power series. And so that wouldn't be valid. It might be valid, I don't know, but it hasn't been proven to us. So it needs to be the case, whatever you do to both sides of the equation, as long as whatever you're doing is already proven mathematically to be correct, right when you do that, either you differentiate both sides or integrate both sides or multiply or divide both sides by something. Once you do that, right after you do that, do you end up with a function on one side and a power series on the other side? Then you can set those equal. Okay, let's take a look at this example. So it says, do f of x is equal to sine of x as the sum of a Taylor series centered at pi over 3. So we just did the Maclaurin series here. Now we're going to do the Taylor series centered at pi over 3. So here you go. They make two columns, write out the first few derivatives, then they plug in pi over 3. And you just do however many of these you need to see the pattern, if there is one. Okay, so they're going to need to, it's not simple enough to where you can just go straight into the, like e to the x at 0, which it was always 1, so you could just say, okay, this is 1 over n factorial, right, to evaluate the coefficient. Well, here you can't just do that. It's not that simple, so they have to write out the first few terms. They include like the x minus a to the n. They write out the first few terms, and then you just have to look for a pattern. And sometimes the pattern is not as simple as other times. Here, this is a little more complicated. And so what they end up doing is they separate this into two separate power series, the sum of two separate power series. One with the odd powers on the power term and one with the even. Or this is the even, this is the odd. Okay, and we're going to work example problems like this, finding power series representations for functions that are where it's a little more complicated to find the pattern. But so it just sets sine of x equal to this, but it says that remember that we have to do this proof that sine of x is equal to this, because we have to do the proof from scratch, because this is a new center point. We proved sine of x is equal to its Maclaurin series, but this is a different center point. But it sets it equal because it says the proof that this series represents sine of x for all x is very similar to the Maclaurin series. It says just replace x by x minus pi over 3 in equation 14. So this is equation 14. You just have r sub n to the x minus pi over 3. So yeah, you could imagine it's going to end up being like the exact same proof. Everything's going to work mechanically the same way. It's just you're doing it with x is x minus pi over 3 instead of x. Okay. This paragraph is just stating, it's clarifying how that when we differentiated both sides and multiplied both sides by x, how could we state that those were equal without having to prove it? And also, what they also state that I actually forgot to mention is that, so once we differentiated or multiplied both sides and we got that the function was equal to the power series, not only is that equal to that power series, but we know that what the coefficients of that power series must be. They must be that c sub n is f to the n. Like, it's not like we could, if we integrated in some unique way, we would get some other power series representation for the function. No, if a function has that was the original theorem, if a function has a power series representation, so like the function is equal to a power series, then every time, no matter what, the coefficients are going to be this. It's not like they're saying, it's not like because we differentiated it. It's not like because we didn't build it, the coefficients from scratch, but instead we differentiated it or integrated it or whatever, that we're going to get some different coefficients. No. Okay, the next example is about the binomial series. I'm actually going to go over that in the next video, but if we skip ahead past the binomial series, here they give a table. It says some important Maclaurin series and their radii of convergence. These are all Maclaurin series that we derived in either this section or the previous section, except for we haven't talked about the binomial series yet. So here's from the previous section, the geometric series with first term 1. Let's see, we derived all these. Arctangent of x and natural log of 1 plus x we found in the previous section. That came from like putting this, like replacing x with like x squared, and then the integral of that was arctangent of x, stuff like that. Okay, and again, you can think about why it would be potentially valuable to have a list of just Maclaurin series. That's what I was just talking about a few minutes ago. You know, especially if the Maclaurin series has a large radius of convergence. In this case, I guess it's not quite as valuable because here the radius is 1. So if you needed to evaluate arctangent at x is equal to 3, you'd have to make another series centered at 3. But if it has a large radius of convergence, then, you know, with a computer, you know, if you could plug in big values of n, you don't need to think about, oh, if I want to do sine of 12 or e to the 20 or something like that. You don't have to necessarily make a new power series or a new Taylor series centered at that value. You could just plug in that value and use a bigger n than you would normally use. And again, especially when you consider when we did convergence or partial sum estimates earlier in the chapter, we would just like manually do n is equal to 10, and we would get really good accuracies. We were doing that manually. Imagine with a computer where you could put in n is equal to 100 or 1,000, right? Okay, but so this video is titled Creating Taylor Series of Functions, because what we're going over is, so in the previous section, we started with this 1 over 1 minus x, this power series, and we learned the mechanics of creating offshoot power series from this. You know, finding similar forms. And so like if you had 1 over 1 minus x squared, you could replace x with x squared here, things like that. And then you could differentiate both sides, integrate both sides, and just find other power series representations of functions. And so what we're doing in this section is we're taking those concepts and applying them to not just this power series, but any power series that we have. That's what we did with we found sine of x, then we differentiated to get cosine of x. We multiplied cosine of x by x to get another power series, to get the x cosine of x power series. Okay, so that's the general idea. You can create a power series from scratch, from the basic basic formula, prove that function equals its power series, and then create offshoots from that power series, just like we did with in the previous section. Now, in all of the examples we've worked in this video, we haven't worked an example like a pattern matching example. That's what I'm calling it. But what I mean is that, so we're going to see an example in a second. If we wanted to get the power series representation for e to the minus x squared. So we could do this from scratch, but if we look here, we could just plug in minus x squared. Simplify the power series formula, and we get the power series representation for e to the minus x squared. That's what we're going to do here to integrate e to the minus x squared as an infinite series. Okay, now you might be wondering, well, what are like the rules for that? You know, it's like it doesn't seem like you could just do that for no matter what. You know, I could put some crazy function e to some crazy function. Can I always just do that? Well, the answer to that is yes. You can really, you know, as long as you know how that function you have up here works, right? You can't just put some weird function up here that you don't even know what it is. But whatever you could do that for any situation. But what's going to happen is, though, the way you have to look at it is you'll make the substitution, and then you're going to go to this is similar to with differentiation and integration of both sides. You're going to go to the power series and you're going to simplify it, and it needs to be, whenever you're done simplifying, it needs to be equal to once again a power series for all n values. If it turns into something else, then we haven't proven that you can do that. Right, we saw examples in the separate video on dedicated to just talking about differentiation and integration of power series. We saw examples of, you know, if we multiply both sides by something, a certain function, it turns it's not a power series for the first two terms. It's only like from n is equal to 2 to infinity is it a power series, and that's fine. You can perform. It doesn't mean you can't differentiate, and it's not valid that way. However, when it comes to differentiating it or making a substitution and then saying that's equal, setting something equal to that, we haven't proven that you can do that. So when you make the substitution and simplify, it's still a power series for all n. You know, you might use an extreme example and say, well, could I do e to another power series? E to the power series, this power series at arctangent x? Yeah, you could. And why can you do that? Because remember, as long as you know, you'd have to update the domain. You know, if e to the x had domain restrictions, it would be like a combined domain restriction. But a power series, as long as you're inputting an x that's within the radius of the interval of convergence, a power series is just a number. X is just a number. A power series is a number once you input an x within the radius of convergence, or the interval of convergence. Now, you'd have to put that into a computer program, because the idea would be for every n value, you go to that to evaluate that term. You have to do another power series for that at each term. So it'd take a lot of steps to do it, but a power series is a number. X is just a number, right? So sine of x cubed, you just replace x with x cubed and simplify. Sine of x to the minus 3, my guess is that would end up simplifying to it's not a power series for the first couple of terms. And so then you can't really say that. Now, again, what do I mean it's not a power series? If it's a power series, then every single term has to be some constant coefficient out front. It doesn't have to be the same coefficient for every term, just a constant, a number out front, multiplying by an x minus a constant, plus or minus a constant, to a positive integer power, or 0. It has to, every single term has to be of a form like this. Like you couldn't have minus x. I mean, you could have minus x. The reason why is because you could do some algebra to simplify it and put it into this form. But you have to be, no matter what, you have to be able to do some algebra and put it in every single term into a form exactly like this. If you have any term that's not like this, then it's not a power series. Okay. So, but here's an example where it's a pattern match, but they're actually matching up the patterns of the series expansion. So they say find the sum of this series here, and so what they do is they find an a sub n representation for this, and they get that. So here's the series, and so now they're comparing this a sub n to the a sub n's, not the functions, and you can see that this has the same form as this here, right? X to the n over n, but the x is 1/2. So this is natural log of 1 plus x. natural log of 1 plus 1/2, that's natural log of 3/2. And 1/2 is within the radius, it's a valid input. You can only input anything from between 1 and -1, but they don't say anything about the endpoints. Okay, one reason that Taylor series are important is that they enable us to integrate functions that we couldn't previously handle. In fact, in the introduction to this chapter, we mentioned that Newton often integrated functions by first expressing them as power series and then integrating the series term by term. So here's the function e to the minus x squared. This can't be integrated by the techniques discussed so far because its antiderivatives are not elementary functions. Yeah, we talked about this in chapter 7. There's a lot of most antiderivatives you can't evaluate by normal means. But here's one that you couldn't evaluate by normal means, but we could integrate it as an infinite series. So evaluate this integral as an infinite series. So again, you could do this from scratch, but consider doing like a substitution. So we put minus x squared into e to the minus x, or e to the x, and they substituted in. So they substituted in minus x squared into this power series, simplify, and get this. So you see from you're starting from n is equal to 0, you haven't changed the start point, and you have a power series. Every term is the same form as a power series, so that's fine. You've got the power series representation for e to the minus x squared. So now we know how to integrate a power series. They integrate, and the series converges for all x because e to the x converges for all x. Okay, now as far as the c, the integration constant, remember you can't. This is it. You can't get the integration constant for this scenario because we don't have a function. It was only the case if we had but previously we were integrating 1 over 1 minus x. Well, let me do this. We started with 1 over 1 minus x. And then we were integrating both sides, but we could get this integral. So we got something, I forget what it was. Maybe it was natural log of 1 plus x. I don't know. Or no, 1 minus x maybe. It was minus something like that. And so that was equal to the constant plus the power series, where we could plug in x is equal to the center point of the power series on both sides and solve for c. But here it's different because we can't get this integral. Okay? Now they wanted to do a definite integral of e to the minus x squared from 1 to 0. So the idea is you're plugging in 1 into the power series and then subtracting that from when you plug in 0 to the power series. Well, every term other than the c has an x in it. So when you plug in 0, that evaluates to 0. The integration constant isn't a fact. It doesn't come into play with a definite integral. So the definite integral is just this evaluated at x is equal to 1. So they plug in 1 and they get, so here's, if we come back to the integral, they perform the integration and then write out the first few terms, and then they can see the pattern and get an a sub n for the integral. So that's the sum from n is equal to the starting point wouldn't change, 0 to infinity of this a sub n is the integral. So this is an alternating series, and so when you plug in x is equal to 1, you get so the definite integral is this series here, but with x is equal to 1. So when you plug in 1, what do you get? It's like plugging in, you're plugging 1 in here. So with that, you get a series without an x in it, just like we worked on in the first few sections of the chapter, right? With all the different convergence testing, you get one of those with just an a sub n with no x. And so that's an alternating series, and you can use when x is equal to 1, you plug it in, you use the alternating series test to show it's convergent, and then you can do a partial sum with they do the first 1, 2, 3, 4, 5. But I want to stress, with a computer, you could do 50 terms, 100 terms, right? And then they use the alternating series estimation theorem to show what the error is. Just the first 5 terms, the error is magnitude is 0.001. Okay. Another use of the Taylor series is illustrated in the next example. The limit could be found with L'Hopital's rule, but instead we use a series. So they illustrate an example here of evaluating a limit using series, even though this could easily be done with L'Hopital's rule. They're just illustrating this as an application. So the Maclaurin series for e to the x, Maclaurin series because x is approaching 0. So they write out here's the Maclaurin series for e to the x. They write this out with the first 4 terms. And so minus 1 minus x over x squared. And then you think about distributing dividing x squared by each of these terms. And, well, no, okay, so 1 minus 1 is 0, and then this is x. X over 1 factorial is x, so x minus x is 0. So they take out the first 2 terms from the numerator, and now they're left with this. Now they divide x squared by each term, and they get this new series. And then as x approaches 0, every single term goes to 0 except for the 1/2, and there you go.